Hello, everyone. Welcome to part 2 of our Designer to Analyst series. I'm the moderator, Krista Prokos. Before we get started, I want to let you know that you can submit questions for today's presenter by typing them into the Q&A panel at any time. We'll collect them and address them at the end of the presentation. And now I'd like to introduce our presenter. We're happy to have with us today Sasi Sithambaram from Dassault Systèmes SOLIDWORKS. Sasi, take it away.
Thanks, Krista. So let's go ahead and jump right into the webinar today. So for today, we're going to talk about nonlinear analysis as an extension of yesterday. So we're going to continue on our example that we used, that I showed you yesterday as a teaser. And we are also going to pivot and talk a little bit about IoT devices and how we are preparing our simulation product line for the exponential growth of smart products. So let's touch quickly on types of nonlinear. So it really can be broken down into 3 categories: geometric nonlinear, material nonlinear, and boundary contacts. These different categories or different types of nonlinear can exist together or independently. So, for example, of geometric nonlinear, so here we have a long and slender component, and you can see the way it deforms. This is very much a nonlinear behavior. In this next example, we have a nonlinear contact problem of a set of gears. And lastly, we also have the most common type of nonlinear, which is material, where if you have a plastic material or hyperelastic material, viscoelastic material, this all falls under nonlinear. So this is certainly an extension from yesterday when we talked about additive manufacturing. So as we all know, additive manufacturing uses parts that are very much behave in a plasticity manner, and to be able to validate these types of analysis or components of 3D printed parts, we typically would use a nonlinear analysis. So let's talk about the example that we're going to use today. And what we have here is it's a BME, it's a speaker. And we are going to run a 3-point bending test on the chassis of this speaker, which is made out of plastic and possibly even 3D printed. So simplifying the assembly, you can see that we only have the chassis that's left. And to simulate that 3-point bending test, we've included 3 rods, 2 of which are fixed, and 1 will be pushing right down the middle at 20 millimeters. And the material that we're using here is Arclic, and it is a bilinear material. And the rods are going to be alloy steel. It's not too concerned. We're not too concerned about what material the rods are, as our only goal here is to deform the plastic base here. So this is considered a nonlinear analysis, and in the past, we have certainly been able to do a lot of these in SolidWorks simulation nonlinear analysis. However, as we are stepping into a more advanced stage of designing components with much more complex material, we are starting to look at higher end simulation. So our parent company, Dassault Systèmes, has always had Simulia, which carries the Abacus simulation brand, which, as many people know, is the most powerful structural simulation software in the market. So what we've done is having this partnership, and being under that same umbrella, the same company, we've been able to take some technology from Simulia and integrate it into the SolidWorks simulation product line. So we've introduced Simulia Structural Simulation Engineer as an extension of SolidWorks simulation. It runs directly on the 3DX cloud platform. However, all your setup will be directly from SolidWorks. So it'll be as if you're running the simulation from SolidWorks. So let's go ahead and take a closer look at that. So here you can see that add-ins panel within SolidWorks. And we have an add-in right here, which is the 3D Experience Simulation connector. So by turning that on, that allows you to send your simulation parameters from SolidWorks simulation directly onto the Simulia Structural Engineer, or as we are calling it, SSE. So let's take a closer look at this, as we call it a one-click connect directly from SolidWorks simulation. So here we have the chassis that is already set up within SolidWorks simulation. So you can see to the left of the screen all the material, all the fixtures, which is the rod, as well as the translation of that rod down the middle to create that bending, are all, as well as meshing, have all been set up within SolidWorks simulation. Now, to solve this complex nonlinear analysis, as opposed to using SolidWorks simulation, we've decided to take that one step and run it, that one step further and run it in SSE. So you can see to the right of the screen, there is a tab that appears when you turn on the add-in. And this is the 3D Experience Simulation connector. This allows you to bring all your parameters, your material, fixtures, connections, loads, mesh, and mesh control directly into that 3D Experience interface. So there's no setup involved, although you're running a much more complex nonlinear analysis. So we've made it very, very simple for our existing SolidWorks users to use this high-end Abacus technology. So you can see the green check marks here essentially verifies that all the parameters are being transferred over. And we can select the Create Simulation tab. And this will bring all the parameter and set up the analysis in SSE. So just to reiterate a little bit about what SSE is, it's integrated within SolidWorks. It uses the Abacus FEA solver, so it's very powerful. It has a wider range of material models, robust contacts, advanced meshing tools, and suitable for highly nonlinear static analysis. However, we'll also plan to introduce more tools in the next few months that go beyond just static analysis as well. Solve large models remotely with cloud computing, so you can choose to solve this locally or on the cloud, which will free up some space on your computer. And you can easily share and reuse data and knowledge because it's all within that 3D Experience platform, where you can send logins to perhaps even your customers and other people in your team and in your company for to share that data. So here's a preview of how it looks within the 3D Experience platform once you've transferred over all the parameters. So this is the simulation environment. And right now what you're looking at is just a Windows, an Internet Explorer or a Google Chrome. It's just a web browser. So this runs directly from your web browser, and there's no latency issues, as there is also a local installation that drives this as well. So setting up, changing your parameters, and introducing even new mesh capabilities. Once you are in this environment, you can further uh, include more parameters that is part of SSE. So a few things to highlight is the ability to run different types of meshing, such as hex meshing and brick meshing, sweep meshes. These are all not available as part of SolidWorks simulation. You also have very high-level contacts between materials, and we can see here in this panel all the parameters that were automatically transferred over from SOLIDWORKS simulation. Using SSE, we are able to solve quite a bit of complex analysis. So here are a few examples. So if you were on our webinar yesterday, you might have already seen this. So just to dive a little bit deeper, we are able to solve large strain, plasticity, complex contact models, any applications that involve rubber isolator, contact with friction, and large deformation, fluid cavities interacting with structure, as well as hydroforming as well. So any type of stamping application would be able to solve using SSE. Same workflow as SolidWorks simulation, leverages advanced technology, easily solve complex problems. So let's take a look at some results that we've captured using SSE. So you can see here, this is being solved and played in real time within a web browser. So you can run this from any type of computer, even a MacBook, your iPad, anything that can run a web browser, you'll be able to run and solve these simulations. So this is the displacement plot, and this is the stress plot for this analysis. So because this analysis or SSE, the application itself, runs off the 3D Experience platform, we can take advantage of other applications as part of the 3D Experience platform that comes with SSE. So one of those is 3D Play. So in this video, what we'll see is this is your dashboard where you can populate this with links to basically anything you want. You can have our design tool XDesign as a panel as well, and you can have 3D Play, which allows you to save your plots, your result plots, and animation results, and you can access these at any time. So if you want to view your simulation results, you don't have to open up your simulation analysis or reopen your simulation analysis. All you need to do is just access 3D Play to view all the different animations and the different plots. Now, the best part to this is you can share these animations and plots to anyone that has access to the 3D Experience platform. And being that you are the admin of these results, you can give permission or take away permission for these animations and plots. So, for example, if you're running a simulation for a customer, you can share all your results in real time on the 3D Experience platform to your customers, and they can view these again from their iPad, from their MacBook, from any web browser, and give and share feedback using our Messenger app as well. So they can type in any notes and send that off to you based on these results. So flexible solve options, enhanced visualization tools using the combination of SSE and tools like 3D Play. Solve problems much faster because it does solve off within the cloud. And like I said, if you prefer to solve it locally, that can also be done. You have access to using multiple GPU and multiple cores. So if you have a computer that has 8 cores, you can certainly use that, which will allow the simulation to solve much faster. So that concludes the nonlinear portion of this presentation. And now let's pivot to IoT challenges. So today, IoT and smart devices can be found everywhere. Think of your smartwatch, your Fitbits, your Alexa, your Google Home. These are all smart devices. These devices are a combination of mechanical design, electrical design, electronic design, and of course, using the technology of Bluetooth and the internet, all these devices are connected. Today, you can turn on your lights by simply asking Google Home to do so. I can transfer all my um, physical data from my Fitbit after I go to the gym directly to a spreadsheet to keep track of all the different properties that you have within your smartwatches. However, with this technology and certainly growing very quickly, there are some challenges that come with it. For one is electronic packaging. We want these components to get smaller and smaller. Think about your cell phone. We have more and more technology being included into cell phones, but we can only have it be so big. Um, as we've seen over the years, cell phones have started to become bigger in size, but it will never be any more bigger than what you can fit in your pocket. So there is a limitation there to the size. Thermal performance, as these small components and with added capabilities, there is a possibility of it heating up. UL testing standards, so all these components have to pass UL testing standards, and if it does not, it will never see shelf space. And of course, because of how these IoT devices work, it is a combination of mechanical and electrical, electronic. It requires engineering team collaboration, which a lot of time it is a challenge, being that we are in a global economy where you could have one team in the U.S., another team in the opposite side of the world. So how are we going to address all these different issues? So let's start with thermal management with computational fluid dynamics. Thermal management can really be categorized or fall into three different types of thermal um, properties: conduction, convection, or radiation. Again, these three properties can exist independently or together. Flow simulation is our CFD solution as part of SolidWorks that allows you to test for conduction, convection, and radiation, and also integrate other properties such as PCB generators, acoustic levels, um, exchanging information between ECAD and MCAD, testing out non-Newtonian fluids and rotating components. So it goes much more beyond just the conduction, convection, and radiation. So understanding heat transfer modes, address heat challenges with SolidWorks flow simulation. So let's take a look at an example. So here we have a smart refrigerator where can you say today these are already readily available where you can talk to your refrigerator, ask your refrigerator to remind you to buy milk when you go to the when you uh, get to the grocery store. So this panel, if you look in the back of this panel, the PCB, there's quite a bit involved. There is many components, many chips, and we can see in this image all these different components on the PCB generate some form of heat. So we need to account for all these different heat. We can set all this up within SolidWorks Flow Simulation. And as we are running the analysis, we can even monitor how the heat is building up within the enclosure and how it's dissipating. Once the analysis is solved, you can even view animated plots such as your airflow. So in this case, we can see how the air, and this is simply natural convection, is being transferred within the system. Here's a plot of the heat distribution within your PCB. And of course, your heat sink is going to hold on to the most heat because that's its main function. But what we've realized here is that because of the way that the airflow is moving, the cooler air is passing over the heat sink before it touches the capacitors over it. So the capacitors on top of that heat sink is reaching a temperature of 107.6 Celsius. This may be pushing the minimum or the maximum requirements for that capacitor. So we might be overheating those capacitors. So one thing that was proposed is perhaps we can add ventilation on the top to release hot air that is building up between the top of the enclosure and the heatsink. Now, because SolidWorks and Flow Simulation is fully integrated, you can make design changes and run your analysis all within that same design interface. So making design changes are quick. We make a quick design modification. We added ventilation on the top, and because of that ventilation, we are confident that the airflow might be a little bit better, so we are able to push back on the enclosure height as well. Another thing that was proposed in addition to the ventilation is to move the capacitors below the heatsink. Now, as a mechanical designer, this is a very simple decision to make, but these are the types of decisions that you have to collaborate with other teams, such as the PCB designer. So it's not as simple as saying, let's move the capacitors and let's solve the problem in that sense. So this is a major challenge when it comes to solving these types of engineering problems. And in a few slides, we'll take a look at how we can solve this problem easily. So in addition to running the analysis, running the single analysis, we can also run multiple analysis using using a combination of configurations. So it's important to make a comparison of results before and after to ensure that if you're adding a feature such as ventilation, it makes sense, because this is going to drive up the cost, but that cost has to make sense. So by cloning the original analysis, you can have multiple analysis here. So you can see I have 5 analysis, and the first analysis is the default analysis I ran, and the second analysis is with the vent. And I can solve all of these using a batch run. So let's say if I have 5 different versions to my enclosure, I can run all of these overnight, and when I come back in the morning, I have 5 sets of results that I can evaluate, compare, and see what enclosure design might make most sense for my application. You can also run parametric analysis. So for example, if that enclosure size is a concern, so maybe I wanted to try a few different sizes and see how that might affect my results. You can see here I would like to run 4 different enclosure sizes at 40, 60, 80, and 100 millimeters. And I can run this again, just like the batch run, in one go, and I can evaluate what size, what parameter there makes more sense for my application. And of course, all of these can be exported to Excel. So evaluating the final results, we're able to reduce the heat by 12% by including that vent. Because of that added ventilation, we were able to reduce the back enclosure height. Moving the capacitors below the heatsink did increase the heatsink temperature by 0.5%, but that's okay. That's the whole purpose of a heatsink. But we were able to reduce the capacitor by 5 Celsius, which is a significant savings in that temperature plot. So because of the reduction of the heat that's being generated, we're able to reduce the power requirements 25% across the board by just making some simple changes. So just to summarize the results, added ventilation minus 12%, minus 1% for the back spacing, and so on. So now the final challenge here that we have is that as a mechanical designer, I've made a decision to move those capacitors. Now I'm not 100% sure if this is something that can be done in the PCB design. So I'm going to rely on my PCB designer to make that final decision for me. And we can do that by using SolidWorks PCB, which has a direct integration with SolidWorks Flow Simulation. So let's go ahead and take a look at this video. And in this video, we can see I'm making those changes based on my flow simulation results. I've moved that capacitors down underneath the heatsink. And to the right of the screen here, you can see that I'm writing a note to the PCB designer to explain why I made that change and does it make sense. Now, as soon as the PCB designer opens up the SolidWorks PCB, he will get a notification from me that I've written about why I've moved the capacitors down, and it's based on my flow simulation results. And if it does make sense from a PCB standpoint, then please make the changes. Not only the PCB designer can see the capacitors in the new location, he can see the animation of moving the capacitors from its original location to its final location. So making this and tracking the changes much easier. Finally, the PCB designer said that the capacitor movement makes sense and can be done. So all he needs to do at this point is just update the nets. And now we have a completely new PCB. And all of this was done using the collaboration between mechanical and electrical designers. So the SolidWorks Flow Simulation addresses the thermal heat concerns for your electronic products. And you can even run analysis based on the UL testing standards to ensure that you will pass those tests when you have the physical product. And using the collaboration of our different tools such as SolidWorks PCB and Flow Simulation, we can now create that collaboration between our mechanical designers and electronic designers. So streamline that communication process, and of course use that ecosystem that we've built. So what I've shown today as part of that SolidWorks Flow Simulation is the ability to run an internal analysis within the enclosure, but You can also run an enclosure analysis. So if you like to see how the air is being distributed outside of the enclosure or how the air is moving into the enclosure, that can be done as well. You can check to see if your flow is laminar or turbulent. Of course, heat transfer was a big part of the example that was shown. Parameter optimization. So again, that enclosure height, if you wanted to test some different heights, we could do that. E-drawing support. So all of these results can be saved out and viewed in e-drawing. So again, if you have a customer that does not have access to flow simulation, but you would like to share results, you can send them e-drawing. You can send them files that can be viewed in e-drawings, which they can actually manipulate and rotate and view in a 3D form. So if you're interested in testing out some of the tools that I showed yesterday as well as today, there are many different ways we can approach that. Some of these tools are available within our SolidWorks online product trial. So you can give that a try. So if you just go to my.solidworks.com/try-solidworks, you can just simply sign up and you can see what tools are available. So yesterday I showed topology optimization, and you can certainly go ahead and give that a try right away. And I'm going to hold this screen for a second here if you wanted to take a picture of that QR code. And to learn more about everything you've seen from yesterday to today, you can just simply go to www.solidworks.com/category/simulation solutions. Again, I'll just leave it up for a second here so for you to take a picture of that QR code.